In this video, we're going to look at the examples in section 1.3. We're starting with Fibonacci's rabbit problem. A man put a pair of rabbits in a cage. During the first month, the rabbits produced no offspring, but each month thereafter produced one new pair of rabbits. If each new pair thus reproduces in the same manner, how many pairs of rabbits will there be at the end of 1 year? Okay, so I am going to come over here and we'll look at this. I've started this already. I put the first couple of months of information in here. So in the first month, there is one pair at the start, there are no new pairs, and then there's a new pair at the end. There's one pair at the end. In the second month, there is one pair to start. We get a new pair, and then there are two pairs at the end. In the third month, the first pair of rabbits starts reproduces again, but the second pair hasn't been there a full month yet, so they aren't reproducing yet. So we get one new pair, and we've got a total of 3 pairs of rabbits at the end of the third month. In the fourth month, we start with 3. Now we get 2 new pairs of rabbits. That gives us a total of 5 pairs at the end. We start this month with 5. 3 of them will reproduce. We have a total of 8 pairs at the end. We start this month with 8. 5 pairs will reproduce. And we have a total of 13 at the end. We start here at 13. 8 pairs reproduce. 21 pairs at the end. 21 pairs plus 13 pairs gives us 34 pairs. 34 pairs plus 21 pairs gives us 55 pairs of rabbits at the end of month 9. We have 55 at the beginning of month 10. We get 34 new pairs. 34 plus 55 gives us 89 pairs. 89 pairs plus 55 pairs gives us 144 pairs at the end of the month. 144 pairs plus 89 pairs gives us a total of 233 pairs at the end of the year. Slide that up a little bit because I think it's not quite appearing on the screen properly. There we go. That's it for that problem. Let's move on to the next one. In this problem, for 3 consecutive days, Ronnie set up a booth at a craft fair. On the first day, he tripled the amount of money he brought with him, but spent $12 at another booth. The second day, he brought the money with him, doubled it, and spent $40 at another booth. And on the third day, he again brought the money with him, quadrupled it, and spent nothing, and ended up with $224. How much did he bring with him the first day? Okay, so we start with this information. First day, he tripled his money and spent $12. The second day, he doubled his money, spent $40. The third day, he quadrupled his money and wound up with $224. So we can start with the fact that he had $224 at the end of the third day. And then we undo the last thing done to his amount of money. We divide it by 4. Okay, well, 224 over 4 is 56. That brings us back to the second day. The last thing he did on the second day was spend $40, which gives him 96. And then he had doubled the money, so we divide that by 2 to get the amount of money he started the day with. That would have been 48. On the first day, he spent $12. So we add 12 to this to get 60. And we see that he tripled the money he brought with him. Divide by 3 and get $20 that he started with. Next up, we want to find the birth year of Augustus de Morgan, who was a mathematician who lived in the 19th century. He made the following statement: I was X years old in the year X squared, and we want to know in what year he was born. Okay, so since he lived in the 1800s, we can note a few things. The first is that 40 squared is 1,600, and 50 squared is 2,500. Therefore, his age must have been between 40 and 50, because he was X years old in the year X squared. Okay, so now we consider what we want to find: a square number between 1800 and 1899. He was born in the 19th century. So, okay, I guess that's technically 1801 to 1900, but neither of those years are actually squares, so we don't have to worry about those endpoints. We just have to test some values. Let's try 42. 42 squared is 42 times 42 is 44. Sorry, is 4. 2 times 2 is 4. 4 times 2 is 8. 0. 4 times 2 is 8, and 4 times 4 is 16. So we get 4, 6, 17, 64. That doesn't work. So let's try 43, because that's pretty close. 43 times 43, we get a 9. 4 times 3 is 12. 3 times 4 is 12, carry the 1. 16 plus 1 is 17. This gives us 1849. De Morgan was 43 in 1849. And we can say for sure that that's the case because the difference between 1764 and 1849 has to be less than the difference between 1849 and the square of 44. So all we have to do to find his birth year is subtract 43 from 1849, and we get 1806. De Morgan was born in 1806. Next up, one-fourth of a herd of camels was seen in the forest. Twice the square root of that herd has gone to the mountain slopes, and 3 times 5 camels remained on the riverbank. What's the numerical measure of that herd of camels? Okay, so because 1/4 of the herd is in the forest, we know that the number is a multiple of 4. We know this because we can't have a partial camel. Partial camels are messy. If we don't have a number divisible by 4, we wind up with a partial camel, and it's bleeding and it's gross and there's blood everywhere and yuck. Okay, no partial camels. Likewise, we know that there have to be a square number of camels, because if the number is not a square, again, we wind up with partial camels and yuck. So square numbers that are multiples of 4 are squares of even numbers. So we've got 4, we've got 16, we've got 36, we've got 64, and so on. Now, we can right off the bat say that there are more than 4 camels in this herd. We can say that because there are 3 times 5, which is 15 camels on the riverbank. We can also say that this number must not just be a multiple of 4, No, never mind. Ignore what I'm saying. Okay, it can't be a multiple of 8 is the other thing I'm trying to say here, because if it's a multiple of 8, we won't get an odd number of camels if we take away a fourth and twice the square root, because we already know that the square root of the number has to be even. I can cross 4 off because that's way too small. I can cross 16 and 64 off. We can try 36. If we try 36, that means that 1/4 of the herd is 9, plus twice the square root of the herd, that's 2 times 6 is 12, plus 15. Okay, well, 9 plus 12 is 21 plus 15, which is 36. There are 36 camels in the herd. Moving on. The digit farthest to the right in a counting number is called the ones or units digit because it tells us how many ones there are in the number when grouping by tens is considered. What is the ones or units digit in 2 to the 4,000th power? Now, off the bat, this sounds like a terrible problem because we don't want to multiply 2 by itself 4,000 times. That's going to be a very large number. But there's an easier way to do this because we can find a pattern if we look at powers of 2. 2 to the first power is 2, 2 squared is 4, 2 cubed is 8, 2 to the fourth is 16. 2 to the fifth is 32, 2 to the sixth is 64, 2 to the seventh is 128, 2 to the eighth is 256. And I can keep going a little further. I'm not going to go much further. 2 to the ninth is 512. 2 to the 10th is 1024. 2 to the 11th is 2048. And 2 to the 12th is 4096. Now, notice that we repeat this pattern. The last digits 2486, 2486, 2486 appear in that order. So we just need to figure out what is 4000 mod 4. And what we mean by mod 4 is what is the difference between 4000 and the next and the closest without going over a multiple of 4. And 4000 is a multiple of 4. So we can see that it must have a last digit of 6. Next problem, an array of 9 dots is arranged in a 3 by 3 square. It is possible to join the dots with exactly 4 straight line segments. Is it possible to join the dots with exactly 4 straight line segments if you're not allowed to pick up your pencil from the paper and may not trace over a segment that has already been drawn? If so, show how. Well, this is totally possible. We're going to do it like this. I draw this diagonal, and then I turn left from here. I could turn up, but I'm going to turn left. And then I draw this segment through here until that's above this part, and then I draw that segment down there. I have drawn 4 line segments. None of them are retraced, and I don't have to, I can do this without picking up the pen. I think I did pick up the pen once or twice because like over here, I went over the place where I should have stopped, but it worked out fine. You can see I could draw this without picking up the line, without picking up my pen. Okay. Last problem. Determining coin denominations. You may have heard this problem before. Two currently minted United States coins together have a total value of 105. One is not a dollar. What are the two coins? Oop, didn't mean to do that. There we go. Did it again. Doesn't matter. Here's the same problem. I've just written it out. And the fact of the matter is, this is a really easy problem because it's a trick of language. One is not a dollar. It doesn't say neither is a dollar. It says one is not a dollar. And since one is not a dollar, the other is the dollar. And the one is the nickel. That's it for this video. If you have any questions, please get in touch.